Hi everyone, I'm Shooting Wang. Today I want to talk about our work on scheduling microservices on heterogeneous cluster. This is a joint work with all my colleagues at UC San Diego. First, let's talk a bit about the background of this work, the trend of microservice and hardware heterogeneity in data center. So here's a story we know about why microservices gain traction these years. Developers, they used to wrap everything they want into a bundle, and then they deploy these monolithic bundle into the data center. Building application in this way is straightforward only if first we're all perfect coders, we don't write bugs, and we have incredible project planning skills. As we don't write bugs and then don't need to add new functionality after deployment, why do we need microservices, right? However, that's not the case for most of us, and people figure that okay, this is not a good way to move forward. We got the idea, then we got the idea of microservices. Application and microservices are decoupled by functionalities into microservices. As you can see in the diagram here, there used to be these blocks tangled together. Now they become these blocks spread out and connected with arrow indicating their dependency. A single microservice has one concern and one job to do. This makes development easier as you can develop, debug, and ship each microservice individually and independently. Okay, enough about microservice. Let's talk about the hardware heterogeneity in data centers. Data centers used to have CPUs, I mean a lot of CPUs, and that's all. Okay, maybe plus the network fabrics and storage devices, but CPU is the only way of doing all the computations inside a data center. With the rise of deep learning, CPU finds its way into the data center as people always have bigger model to train and run. And then FPGAs and ASICs show up. The hardware landscape of the data center changed as more of these non-CPU devices come into it. Okay, back to the microservice. They're now only running on CPUs. We can imagine that microservices will need some acceleration help from these GPUs, FPGAs, and ASIC. I mean, why not, right? So how are microservices different from monolithic applications, or how could they create different performance or deployment issues compared to the monolithic applications? Look at these figures here. The dependency between these microservices are non-trivial, and they are dynamic because uh, different requests can travel along a different route. This complicated dependency creates a new problem for microservices. If one of them clogs the pipe, then any of these requests that plan to pass through it will be affected. It creates so-called back pressure effects, and they can be hard to detect or even prevent. When this happens, it's cascaded to other microservices depend on this clogged microservice. The latency of these affected microservices spike and eventually violate their own quality of service SLA requirements. Facing these challenges, so how do we schedule microservices? Of course, it's always possible to come up with some smart heuristic. Sinan is a recent work that used CNN together with Boost Tree to deal with the challenges. There's also another previous work that used graph neural network with reinforcement learning to schedule Spark jobs. Sinan used CNN predicts the latency of microservices and used this predictive latency further for scheduling. Both of these works shed light on a promising possibility of using broadly machine learning or more specifically neural network to help scheduling. Okay, so how do we want to approach microservices scheduling? We have two ideas here. First, how about let microservice use something other than CPU if there's something else to use, GPUs, FPGA ASICs? Second, how about some lightweight non-neural network ML algorithms that are more explainable? Here we introduce Octopus. It considers CPU, of course, but also GPUs and ASIC for scheduling. Octopus schedule microservices to GPU or ASIC if microservices themselves indicate they want and they can be run on these devices. This is a preliminary work as people may expect Octopus to be smarter or be more automatic when trying to put this microservices to GPUs or ASIC. However, I want to emphasize that Octopus here by its core is just a simple scheduler. and it relies on the information provided by the microservices to do scheduling. Okay, so we mentioned some non-neural network machine learning algorithms. So yes, we decided to try decision tree, which is pretty simple. But more specifically, the reason that neural network-based approach may not work on heterogeneous clusters are two. First, this hardware heterogeneity and data center adds another dimension to the input of the scheduling algorithm. They need to consider not only CPUs, but also other kind of hardware devices. So to accommodate this new dimension, we'll need to add this dimension into the construction of the neural network. And doing so will increase the size of the neural network, which makes it larger. So then our second point, a larger neural network will take more time to train, and more importantly, it will take us more time to do the inference. And this inference will get us the predicted latency. We chose decision tree because it's simple and lighter weight than neural network. So that's the main big reason. The way we deal with the decision tree is that we train the decision tree offline with our generated trace. In the future, we'll try to make it do online training instead. So our decision tree predicts latency of running a microservice on different nodes. It takes parameters from CPU, accelerators, and these dependency of other microservices. Some of these nodes have only CPUs, some of these nodes have ASICs and GPUs. For scheduling, what we're doing here is we schedule nodes with latency lower than a SLO, and we pick one that's available with the lowest latency. Here's a workflow for Octopus. Essentially, there's a series of microservice scheduling requests arrive at this scheduler. The scheduler will either run some of these heuristic or our decision tree-based approach to schedule microservice onto nodes. If a microservice says it can be run on GPU or ASIC, then the scheduler will satisfy that request if there's GPU or ASIC available. Okay, here comes the evaluation methodology for our work. So we implement a SymPy-based simulator using Python. Using Python. This Python-based simulator is not like the most ideal. It has some limitations. We'll talk about that later. The baselines we consider here are first fit, random, and Kubernetes-like. Let's talk about the first fit first. The first fit, what it does is it linearly search all the nodes and schedule microservices onto a node we find that satisfy the requirement. Randomize then is to randomly search all the nodes and schedule microservice onto the first node that can do it. The Kubernetes-like approach here is what we try to mimic Kubernetes when it's doing its scheduling. By first, we run the filtering process, so it filters out nodes that satisfy the requirement. Second, we give these nodes scores, and then finally we'll choose the node with the highest score. So it's basically a filtering and scoring process from the Kubernetes approach. Yeah. After we're done with the baselines and methodology, here are some setup we use. Our dependency data between and among these microservices comes from this social network benchmark of this Death Star bench. It's a paper from SFOS 19. We sample subgraph from this social network benchmark for this dependency, and then these subgraphs are our simulated microservices. Our latency number of running microservices taken from another paper called Nightcore. It provides a pretty detailed latency distribution stats that we can use for our simulation. For microservice that can be run on GPU or ASIC, these are neural network related microservices. We run inference using Onyx with GPUs, and for the ASIC, we run Cycle Accurate Simulator to get the execution time. More specifically, these two microservices we're looking at is an image recognition one and an object detection one. We use MobileNet V2 and YOLO V2 for the MobileNet V2 for image recognition and YOLO V2 for object detection. Here are some results we got from the simulation. We observe speed up of makespan and compare ourselves to our baselines. The workload consists of a collection of jobs, or you can say microservices. More specifically, we generate these using the setup we just mentioned in the last slide. Now, speed up here is for a collection of simulated microservices, not for an individual microservice. As you know, a single microservice is not an application by itself. This speed up here can be attributed to two things. First, we schedule our microservices onto more than CPUs. This gives individual microservices speed up in its end-to-end execution time. Second, our decision tree makes good prediction here. We don't have detailed breakdown of which one is contributing more to the speed up. However, we have to admit the speed up is not trivial. It's there. Yeah. After looking into how Octopus scale with different number of microservices, we look into another axis of scaling. We try to scale the size of cluster with more hardware resources. We cannot evaluate larger size of workload or larger size of cluster because our SimPy simulator has its own limitation. It cannot sustain more than we're showing here. So definitely having a more scalable simulator is definitely on our to-do list. What we're seeing here is that we're not seeing more speed up with more hardware resource available on the cluster. First, it's because we use a fixed size workload and then we're only scaling the size of the hardware resources. Second, with more nodes, it makes the search space of the decision tree larger. It eats out the speed up we have on the makespan. Essentially, this decision tree needs to take in more input, and then the inference time will be slightly higher. Okay, at last, these are our future work and discussion. So besides decision trees, we want to explore more other machine learning algorithms for scheduling. I mean, classic machine learning algorithm, not just neural networks. And also, we want to investigate the robustness of these machine learning scheduling algorithm with larger and more diverse workload. We want to see if it can tackle different types of workload, and also if the workload, the scale of the microservices is larger, then can this schedule handle this? Also, at the end, we want to implement like the entire system, because implementing a system can help us to capture some system level contention, also some performance issue that cannot be well simulated within any kind of simulator. That's all for my presentation today. I'm open to take questions.